Alright, hello everybody, and today we're going to be having a look at this integral. So, integral of x squared over the square root of x squared plus 4. I've actually got asked this integral, how to solve it, and it was a pretty interesting integral. I can tell you that you need to use hyperbolic trig substitution or some other trig substitution to solve it. But in this video I'm just going to use hyperbolic trig substitution because it just makes things a little bit nicer. So let's just have a look at how I can solve this first. Notice that we have x squared plus something, and this something we can just turn it into a 1 later on. But when you have something like that, usually when you use trig substitution, you would substitute, say, tangent, so you get a secant out of it when you do the substitution. But if you look up here, we're also going to get a tangent squared if we do that, and our dx is going to turn into secant squared times some other variable, so it's not going to be very nice. But if we use a hyperbolic trig substitution, I can tell you that it's going to be a bit nicer to do. So first of all, we want to get rid of this 4 here somehow. So let's just take 4 out as a common factor. So I'll just write it here. This is nothing but the integral of x squared over the square root of, and we're going to take 4 out. And inside here, we're going to have x squared over 4, and then plus 1. So if you distribute this, we're going to get x squared, and then 4 comes into here, so you get 4. So these two integrals are equivalent, and this is a square root of 4, so that just becomes 2, so we can bring that out the front. So this becomes 1 over 2 times the integral of x squared over, so this 4 here, we can write this as 2 squared. So we can just write this as square root of x over 2, but squared, like that. And that's the same, and we can just put a plus 1 there. And notice that we have an x on 2 inside here. Ideally, we want this x here to also be x on 2, so when we do the substitution, things are more consistent. So let's just force that to be a 2 somehow. So x squared is the same as 4 over 4 times x squared. And this 4 here, we can write this as 2 squared. And we can bring this 4 up here out to the front. So we have 4 and 2. And 4 and 2 is nothing but 2. So now we have 1 over 2 squared and x squared here. We can combine these together to get a x squared, x on 2 but squared, like so. So now we have an x on 2 and an x on 2 here, so that's very good. We can do our substitution now. We've got my dx here. So we're going to start with our substitution now. So we're going to let this x on 2 be some hyperbolic function. So what function can we make this equal to? Notice that we have x squared plus, so something plus 1. So I'll just write it as, I don't know, u squared plus 1. Whenever you have that, think back to hyperbolic identities. So if you have cosh squared minus sinh squared, that just gives you 1. And you can move this sinh over to the other side, so you have cosh squared equals 1 plus sinh squared. So if we substitute sinh squared for whatever squared this is, since we're adding 1 to it, we're just going to simplify it down to our cosh squared, which is really nice. So let's substitute this for some sinh. So we're going to let x on 2 be equal to sinh of, I don't know, t. There we go. So if we rearrange this, we get x is equal to 2 sinh t. And we can differentiate both sides to get our dx. So dx is equal to 2. Derivative of sinh is just cosh t times dt. And we can throw all this information back into this integral. So we're going to get 2 times the integral. So up here we have x on 2, but we defined that to be sinh of t. So at the top we're going to get sinh of t but squared, and on the bottom we're going to get the square root of sinh squared of t plus 1. and dx turns into 2 cos t dt. So I'm just going to bring the 2 out because it's a constant, so we're going to get 4 out here. Cos of t dt. Alright, so now we have this identity we can work with here. So this now just becomes sin square root of t over the square root of cos square root of t cos t dt. And notice that we have a squared and a square root here, so this just becomes absolute value. But if you know what the graph of a cos looks like that. Cos is always equal to or greater than 1 here. So that means that cos is always positive, so we can actually ignore this absolute value here. So that's a very nice. So because of that, now cos and cos here can cancel, and we're going to be left with the integral of just sin squared of t dt. So this is, we can actually evaluate this using some hyperbolic identities. So let's just rub this stuff here out. I don't need it anymore, I don't think, except for the substitution. So let's just rewrite this a bit. So we have a 4 times the integral of sin squared of t dt. And this squared here is kind of annoying us, so I want to use some kind of identity to get rid of this squared here. So we're going to use the cos double angle identity. So if you have cos of, say, 2t, that's just equal to 1 plus 2 times sin squared of t. Alright, so now if you isolate this sin squared, so subtract 1 on both sides, divide it by 2, you're going to get sin squared is the same as 1/2 cos of 2t minus 1/2. So these two are equivalent. So now we can substitute this part in for our sin squared. So now we have 4 times the integral. Sin squared is nothing but 1/2 cos of 2t minus 1/2. There we go, and tied off with the dt. So now we can actually evaluate each of these parts. So we have 4 times. So when we integrate this, we're going to get some kind of sin of 2t. But remember, when we differentiate that, this 2 will jump down to the front, so we need to counteract that somehow. So we just divide it by 2. So we're going to get 1/4 times sin of 2t, and we can check that when we differentiate this, we're going to get cos of 2t. 2 is going to jump down to the front here because it's a constant, and we're going to get 2 and 4, which is exactly 1/2. So that's good. So we're going to subtract 1/2 t. Alright, so now we can distribute this 4 into everything. So we're going to get sin of 2t, and then here we're going to get minus 2t, like so. So sin of 2t, we can expand this using the double angle for sin. So let me just rub this out. So sin, this becomes 2 sin of t cos of t, and then subtract 2t. So this and this is equivalent. And if you remember back to the substitution, we had x on 2 is equal to sin of t. So sin of t here, we can just substitute x on 2 in. So we have 2 times x on 2. But we want to figure out what cos of t is. And to do that, we can just use some identities to solve it. So if you remember back, I said that cos squared of t minus sin squared of t, that's just 1. So we want to get cos somehow in terms of sin. So let's just isolate the cos. So cos squared of t is 1 plus sin squared of t, taking the square root on both sides. So we have cos of t is equal to the square root of 1 plus sinh square root of t. And we actually know what sinh square root of t is. That's just x on 2. So we have cosh of t is the square root of 1 plus x on 2, but squared. And we can expand this out, so we have x on 2, x squared on 4. And if we multiply everything inside here by 4, we can get rid of this fraction here. So we have 4 plus that. But since we multiplied by 4 in here, we have to divide by the square root of 4, which is 1/2. So this is the same, so we can substitute this back into here. So cosh t is 1/2 square root of 4 plus x squared, and then negative 2t. So t, our substitution was x on 2 is equal to sinh t. So t, if you take the inverse sinh, t is just inverse sinh of x on 2. So yeah, so t, we'll just write that in here, sinh inverse of x on 2. And I can just clean things up a bit. 2 and 2 here cancel, and we're just going to be left with, I'll write it like this, 1/2 x times the square root of 4 plus x squared minus 2 times the inverse sinh of x on 2. And we are done, so we can just put down a plus c. And there we go, that's the answer.